Hi everybody, welcome back to my channel on Feynman integration. Today we're just going to be discussing a very useful theorem called de Moivre's theorem, and in my opinion it's one of the most useful results in using like complex numbers in Euler's formula. And anyway, yeah, it's spelled like this, and I believe it's pronounced de Moivre's theorem. So anyway, from Euler's formula, we know that e to the ix is equal to cosine x plus I sine of x. So we know if we raise both sides of this equation to the n, we get this right here. And we also know that this, using the properties of exponents, we know that this is equal to this, which in turn, using Euler's formula on this, is this. So that's basically it. That's de Moivre's theorem. It's this equals this. That's it. That's what de Moivre's theorem says, and I hope that was easy enough to follow, and I hope you understand why that's true now. So, anyway, we're going to use that fact to find an expression for cosine of 3x in terms of cosine of x. Things like cosine squared x that's okay. But what we don't want to use things like sine x. We don't want to use things like cosine of 2x. It will be all cosine x's. So, anyway, we'll start with this right here. We'll start with cosine of 3x plus I sine of 3x. And it should be no mystery why I chose to do that. It's because that contains the thing we want to find an expression for. So we know that cosine of 3x plus I sine of 3x is equal to e to the 3ix from Euler's formula. We also know that e to the 3ix is equal to e to the ix cubed. Which in turn is equal to cosine x plus I sine x cubed. So, so basically we have this. We have cosine of 3x plus I sine 3x is equal to cosine x plus I sine x all cubed. So let's expand this out. Now what we're going to do is we're going to expand this out and then pull out the real part of this expansion and equate it to cosine 3x, and you can do that. If you have one thing on one side and one thing on the other, both sides contain real and imaginary parts, you can equate the real parts on one side to the real parts on the other side, as well as the imaginary parts on one side with the imaginary parts on the other side. So anyway, what we get if we expand cosine x plus I sine x is this right here, cosine cubed x plus 3I cosine squared x sine x minus 3 cosine x sine squared x minus I sine cubed x. And then since we're interested in the real part of this, the real part of this is cosine cubed x minus 3 cosine x sine squared x. That's it. That's it. That's the real part of this, and that's what we're interested in. So since we don't want to be using sine of x in any way, what I did is I rewrote sine squared of x as 1 minus cosine squared x. So anyway, yeah, now we have from de Moivre's theorem that cosine of 3x is equal to cosine cubed of x minus 3 cosine x times 1 minus cosine squared x, which after the simplification, basically distributing this into here, you'll get, and matching like terms, you'll get that cosine of 3x is equal to 4 cosine cubed x minus 3 cosine x. So that's it. That's you can use de Moivre's theorem now that you know the process to find expressions find an expression for sine of 13x in terms of nothing but sine x. And it would take a while, but why I like using this is because it minimizes the amount of memorization you have to do. One of the reasons I wasn't a big fan of my trigonometry class in high school was because of the ridiculous amount of formulas you have to memorize. And if he had just taught us de Moivre's theorem, we could have come up with all those expressions on our own pretty easily. But anyway, that's de Moivre's theorem, and we're going to be utilizing it probably in a future video. That's it. Hope you enjoyed that.